All right, now for some science. So I had the pleasure of hearing Chandra speak at a user group meeting. I guess I've been to, well, no, it was a seminar at the University of Delaware last year, and I got to see, and it was very refreshing because Chandra was making advantage of Dragonfly tools that we don't promote and document so well, and I didn't know anyone was making use of them, so I was very excited to see it there. And Chandra, you also introduced us to the folks out at the Getty Museum on the dendrochronology project. So we really appreciate you facilitating that with some very exciting research. So, so I guess Chandra is a Dragonfly ally going back a few years. And did you first learn about Dragonfly with the purchase of your imaging equipment from Rigaku, or had you known about it even before then? Yeah, so we rely very heavily on our partners, and we're glad that our partners are able to put Dragonfly in the hands of their customers. So with that, let me give Chandra the podium so she can tell us about 3D analysis of pore systems in archaeological ceramics as a tool to reconstruct production methods and performance characteristics. Thank you, Chandra.
Well, good morning. For archaeological ceramics, it's not possible for us to directly observe the potters making their pots, using them or trading for them, of course. So what we have to work with is the archaeological context, which means the site and the locations within the site where the pieces end up. So that's generally where the object was discarded after breaking or no longer being of use. And of course, we also have the material or remnants of the material itself. Here we see some images from ethnographic research studying modern potters who still work in traditional methods with traditional raw materials, tools, and firing techniques. This, along with laboratory studies with controlled experiments, give us ways of developing hypotheses about how ancient potters may have worked and how they may have intended their products to function. So why do we care about ancient methods and products of potters? Well, ceramics are found at archaeological sites throughout the world. They've been important products for usefulness for people for thousands of years. We find ceramics used for a wide range of functions. They serve as important markers for constructing dating sequences and networks of local, regional, and long-distance trade, and for understanding local styles, technological developments and choices, and a lot of other important cultural issues. While a lot of effort has gone into developing analytical methods for studying ceramic materials, in contrast, very little consideration has been given to pore systems and what they can tell us about ceramic production and use. And yet, the structure of a pore system is strongly related to the raw material selection, processing, and fabrication methods, and firing regimes. So characterizing pore systems can help in identifying groups of similar related ceramics and for determining how well they might have functioned for particular uses. So micro-CT coupled with 3D image analysis is a good strategy for accomplishing this. In contrast, mercury porosimetry can't give us information about isolated pores, which are important indicators of firing techniques and firing temperatures and of use properties. And also then you have to work with and dispose of a very toxic material. 2D methods such as thin section petrography are great for identifying particles that can pinpoint geological sources and give indications about firing changes. But porosity as viewed in 3D is just not representative enough of the 3D material. The pores often extend in 3D in ways that just aren't visible in the 2D images. It's important to keep in mind that what we're usually dealing with from archaeological contexts are small broken pieces from those ceramic vessels in the form of small sherds like we see on the lower right. So I'm using Dragonfly to study pore systems in micro-CT images of samples taken from these small sherds. It's an advantage that we can do a micro-CT scan and then also make a thin section or do other analytical methods on the exact same sample. Since I have limited expertise in deep learning, I use the segmentation wizard, which, as Franklin mentioned, I think makes this an easy process. And I generally only need about 3 slices to get a good model for training on. And once I have a model that's segmenting well, I find that using the image calibration tool helps me be able to reuse it for many similar images, even though we have a lot of variation with archaeological ceramics. So that's a big time saver. And I found that a 5 by 5 millimeter field of view, which for my instrument gives 10 micron spatial resolution, works well enough. A larger field of view will miss too many of the smaller pores, but a smaller one will miss the full extent of too many of the larger pores. And given the variation within ceramic materials from archaeological sites, depending on the material, I do 2 to 5 replicates per sherd, never just one analysis. I've been focusing on the pore systems because they've been neglected in archaeological ceramic studies and can provide a lot of information. I do plan to tackle particles next, but differentiating between the many phases of particles in a micro-CT image is a bigger challenge. I'll give 2 examples of the ways in which I've been using image analysis to study pore systems. The first is for what they can reveal about ancient firing temperatures, and the second is for how they can be used to calculate thermal conductivity and why that's important for determining potential vessel functions. So traditional ceramics are fired at temperatures ranging between about 600 degrees C up to about 1400 degrees C. The lowest fired ceramics are generally made with relatively impure iron-rich clays, coarsely ground and coarsely sieved. The additives are also generally coarsely ground, and you see some of those on the upper and central right. And the main purpose of these is to prevent cracking of the vessels during the drying and firing process. They can include things such as organic material like straw or rice chaff, crushed shells, crushed rocks, and crushed sherds. The firing is usually done using wood as a fuel, and it may be on the open ground with the fuel piled around the pots like was done on the lower left, or in a simple kiln dug into a hillside. The products are unglazed, and they may be covered with a simple colored clay slip or be undecorated. They could also have decorative elements incised, impressed, or applied to the clay surface. Higher fired ceramics may use a clay such as a white kaolin that will vitrify more easily. They're much more finely ground, and they may be levigated in water as well as sieved with finer sieves to remove the larger particles and impurities. And any additives will be finely ground. The firing is done at high temperatures and sometimes for long periods of time using much more complex kiln structures that could be fueled by either coal or wood. And the products are often partially or wholly covered with a glassy glaze. The ceramic body will have some high temperature mineral alterations and glass. And there are many ceramic traditions that fall somewhere in an intermediate area between these low-fired and high-fired extremes. We'll look at just a few examples of the many pore system variables that are strongly related to firing temperature and to fineness of the raw material. The plot on the left shows that total volume percentage porosity is correlated with firing temperature. here ranging from a high of 31% for porosity for a vessel fired at 900 degrees C, going down to 2% porosity for one fired at 1350 degrees C. And some of the variability in between there is probably due to complications presented by choices in raw material processing and fabrication. The plot on the right shows the percentage of pores accessible to the surface and the percentage of ones that are interior only, and those are calculated to give a ratio of surface accessible to inaccessible interior pores. And that's even more strongly correlated with firing temperature at 20.3 for the lowest firing temperature and 0.3 for the highest ones. Here the pores accessible to a surface are in blue and the interior only ones are in red. A low volume percentage of pores coupled with a low surface to interior pore ratio that we see on the right is characteristic of higher fired, finer grained ceramic materials. The lower fired coarse grained ones, as on the left, tend to have greater overall porosity, and many of those pores will reach the surface. Greater porosity is advantageous for cooking vessels, for example, that tend to have a high percentage of polycrystalline components. The crystals can then expand on the cooking fire without exerting pressure that might cause the vessel to crack because the many pores will help absorb the strain. And a high surface to interior pore ratio it can also impact properties. Promoting evaporation, for example, which is useful for storage vessels, and the many large connected pores can help retain heat in cooking vessels. There are many statistical properties of pore size and shape that can help characterize sherds and also impact vessel properties, functional properties, and are also related to firing temperature. So as a couple of examples here on the upper right, the pores are color-coded by a measure of sphericity, and that the plot below it shows it's very strongly related to firing temperature. Higher fired ceramics have more spherical and globular pores. In contrast, on the right, a measure of pore elongation shows the opposite. The highest values are found with the lowest firing temperatures. So taking a lot of these parameters together in a multivariate statistical analysis can help us determine the probable firing temperature for ancient ceramics. Low-fired ceramics, in addition to having greater porosity, also tend to have higher connectivity values, which can be quantified in Dragonfly by viewing the segmented pore systems as graph models of the system, where the spheres represent the pores and the lines between them are the pore connections. And here the higher connectivity values can be partially explained by the presence of many locations where there are intragranular pores in contact with each other and with some intergranular pores in common. And that raises the connectivity values. Because of the partial loss of organic materials, dissolution of partially melted feldspars, cracking of quartz grains, and other firing effects on those large particles that tend to be more numerous in low-fired ceramics. In contrast, at higher firing temperatures, many of those partially melted grains will have completely melted and vitrified, creating a dense, glassy matrix, filling in and breaking up some of those previously connected pores and introducing new isolated round pores as gas bubbles are released during vitrification. The length of connections between pores can also be important, as well as the tortuosity values that measure the extent to which the connection pathways deviate from a straight line. Very high-fired ceramics tend to have significantly lower tortuosity values, for example. If the particles and matrix have also been characterized by petrographic methods, then we can use the segmented 3D image to study various material properties. For example, the Porous Microstructure Analysis Program, or PUMA, is available within Dragonfly, and here it's used to measure the effective thermal conductivity. Starting with the estimated thermal conductivity of individual components, such as the quartz, feldspars, clays, and the air in the pores, and with the segmented image, where the percentages, connectivity, size, shape, and locations of the phases are known, temperature fields are simulated in the X, Y, and Z direction. Then the steady state temperature is solved at every point, and the simulation output gives you the thermal conductivity of the ceramic in watts per meter Kelvin in each direction. Here we see some comparative results for some archaeological and ethnographic ceramics. Traditional thermal conductivity measures are done using laboratory prepared specimens, not on real sherds, mainly because sample constraints generally preclude the use of real sherds. Fairly large, thin, and very flat discs are required. So 3D image analysis is a great addition to the toolkit because it's easy to include any number of real sherds, just keeping in mind that porosity values might change somewhat during use and burial. Here the data and plot show the strong correlation between thermal conductivity and volume percent porosity, with conductivity going up as porosity goes down. So the earthenware sherds with 31% porosity have a mean value of 0.329 watts per meter Kelvin, and the Xing white porcelains at 2% porosity have a value of 0.548. And the points between those are follow a linear pattern. Firing temperature is more complex, though. Other than the lower and higher values, it doesn't follow a linear pattern. For example, the Sichuan teapots that you see on the upper right are made with the exact same raw material that's used for the Sichuan cooking pots and hot pots, like the one on the left. The cooking wares are fired at a higher temperature than the teapots, but have a lower thermal conductivity. The tea-wares, their raw material is ground much more finely, and that's the pile of material that you see in the foreground. Then is the material for the cooking wares, and that's the coarse pile in the background. So this seems to be affecting thermal conductivity. The tea-wares here and the Xing porcelains tea-wares, with their higher thermal conductivity, will readily pick up the heat from the hot liquids poured into them and distribute it evenly, but will then begin to lose the heat to the environment. But that's okay because these are generally for fairly short-term use, just while the tea is being drunk. The cooking pots and hot pots with lower thermal conductivity are good for slow cooking dishes like stews that will sit on their heating source for a while, simmering the contents. They're slower to pick up the heat, but once the pots get warm, they'll retain that heat for a longer period of time because of the many pores that have insulating power. And that hot pot you see there will sit on that dining table for an hour or more while the vegetables and meat are simmering in the hot oil. The PUMA software can also be used to measure permeability, and there are many other pore parameters that can be used to investigate other aspects of production methods and different properties that can impact functional use properties. So we're just beginning to explore the new possibilities presented by using 3D image analysis with Dragonfly to better understand the performance characteristics of archaeological ceramics. Thank you.
That was awesome. Here, watch this. Let's see how impactful and how much cross-fertilization we get from this audience. Show of hands, how many people knew you could do pore network extraction in Dragonfly. How many people have ever seen work of it done or presented by a scientist? Okay. All right, so like 3 or 4 of you have seen Dragonfly pore network. How many of you have seen Dragonfly results from a user who was using Puma to do numerical property calculation? See, you're opening the eyes. See, right? I mean, this is what we get when we get to hear from paleontologists and archaeologists and, okay, anyway. So I'm just gushing because it's so exciting. Do we have questions about Chandra's work? Do we? Okay, we have an hour and a half lunch break, so you guys might want to sit together. But we'll start with at least Natalie's first question.
Okay, so I'm an environmentally anxious person, and my question is: if somebody wants to set up an isolated household in the woods, what would be the starter's kit of ceramics to run?
So the question is, if I'm going to go live off-grid in a shack in the woods and have 0 environmental footprint, what ceramics should I bring with me? How should they be fired and manufactured?
Oh, I think you should make them. Just go down to the river and look for some clay and use that and just do open firing with wood.
And 900.
Yeah. Oh, actually, you can go to 600. Oh, and add a bunch of sand or something like that so that it won't crack when you fire.
Okay. Do we have other questions? Highly practical questions. Let's go to Max.
I was just wondering, before you mentioned that you chose the field of view in your deep learning or machine learning. Did you mean the patch size, or what were you changing to catch all the features?
I think it's a question. So Max doesn't do CT scanning, and so in CT scanning, maybe you want to say something about the trade-off between resolution and field of view to see a bigger texture, bigger context.
Yeah, the voxel size, the achievable voxel size will be related to your field, the size of your sample and your field of view. So I experimented. I spent a whole summer experimenting with all sizes of things and different resolutions, and finally came up with that 5 by 5 millimeter field of view gives me the best situation for getting both the finest pores that I can image on my instrument and making sure I have the largest pores and enough representation to really feel that I'm characterizing the sherd. But even there, I would never do just one scan because there is some variability. The finer grained ones, there's less, but you're safer to do at least 2 of those. When I was working with bricks, I had to do 5 replicates because those are, have a lot of variability.
Now everyone's got questions. Let's go to one in the back.
Yeah, thanks for an interesting talk. What's the size of the volume, or what's the limitation in terms of computation for the Puma simulations?
Okay, so that's a technical question on how big of a segmented image matrix can you do a Puma simulation on, like 1,000 voxels cubed or 50 voxels cubed. Do you want to answer that, or do you want me to answer that?
Go ahead.
I don't want to answer it. Not because I don't like the answer, but I don't know the answer. Let's just connect with Nicola. Nicola, do you want to say right now, or do you just want to connect and discuss?
Well, it depends on the simulation that you're doing. If you're doing continuous fluid virtuosity, you need much more memory than
So some of the Puma solvers are solving different differential equations, whether it's fluid flow or heat transfer in this case, and some of those are more greedy for RAM than others. So that defines your upper limit. I don't know if we have a matrix that tells you how much you can accomplish given memory. It may also depend on how many voxels are in the foreground phase versus background phase. We can explore it with you and maybe give you not any heuristics, but maybe put some ceiling, some boundings on it to help you understand.
I don't know the answer to that, but I can just say that I just used my entire
workstation.
I just have an ordinary computer. I don't have a super computer, and I used my entire scanned area, and it only took 10 minutes, and it was easy to use. So.
I think the thermal computation is pretty cheap compared to some of the other differential equations. Let's do one more. I think, Eva, you had a question?
Yeah, great talk. My sister's a ceramics artist, and one thing that she does is she adds paper pulp to the clay to make it lighter, and she can make really fine structures with it. So I assume it burns off in the kiln and creates a more porous network. Do you see any evidence of, I don't know where she got this idea, but
Do you want to repeat that
see the
question?
evidence of additives that burn off and create these porous
So the question is about a modern potter who uses paper pulp to add bulk to and flexibility to the clay. And do you see any of that? Well, it would, of course, burn out. So depending on the firing temperature, there might be some charred remnants in there, which you can see in the CT scan, or you have, if it's all burnt out, you have pores. But if it's all interior and it's fired in reducing atmosphere, you're going to have carbon chunks in there.
Let's thank Chandra.